Dave Hicks, and today we're going to talk about proton nuclear magnetic resonance, or what's just commonly referred to as HNMR. This is part of my series on looking at and analyzing hydrocarbons. We have hydrocarbons, and carbon is such an amazing atom. It can bond together in so many different ways and make so many different types of compounds. And through chemical analysis, we're able to come up with what the formula is, like, CH4. But we can't always describe how things are put together by these chemical formulas, by the ratios of, how many carbons and hydrogens and oxygens that are bonded together. So how do we know what we know then? And the answer there is we use these other analyzing techniques and get clues from each of them. And then putting all those clues together, we can make our best guess as to how this molecule is actually bonded together. So let's talk about HNMR. So HNMR is a way of causing the hydrogen atoms in a molecule to vibrate. And many times they refer to these hydrogen atoms as just protons because, a hydrogen is really just a proton with a cloud of electrons that's around it, right? They use radio waves, or what they call RF waves, which is kind of a high frequency radio wave. And it causes the hydrogen atoms to vibrate, or what they would call resonate. And so when they find certain resonations of these hydrogens, then it causes an absorption, if you will. Very similar to if we could see the colors, it'd be very similar to us, seeing the different colors that are absorbed. And with this, it's a radio wave, so we can't really see the colors that are being absorbed, but it's basically the same idea. They send different radio frequencies through a sample of this, and then some of those wavelengths are absorbed because that is where the hydrogen atoms are resonating, and so they're using up that energy at that particular frequency, and we're able to see that. They refer to these absorption frequencies as shifts. I'm not 100% knowledgeable on why they specifically call it a shift. I believe that it has something to do with them comparing this to some type of a standard, right? That's true with all of these analysis techniques. We always have some standard in which we're comparing everything to. And HNMR is the same. There is a standard that it's compared to. And this standard, if a proton is resonating at a frequency that is different than the standard, then they would say that that frequency has been shifted. I think that's where the use of that word is coming from. And sometimes, and we'll see this a little bit later on, the computers that do this for us and collect this data for us, they integrate these curves because these curves have a lot of different vibrations. So different atoms, they can interact with each other, and they create what they call duplexes and triplexes of different vibration modes, and this makes the graph looks kind of messy. The spectra look kind of messy, and so the computer can sometimes clean that up by integrating the results, and this makes things look a lot easier for us to comprehend. So this is all about measuring what we call a proton environment. The environment of a proton has to do with the carbon atom to which that proton is attached. So different bonding situations, different environments pull on the electron cloud in different ways. So different hybridizations of the carbon. Maybe there's other atoms that are attached to it, more electronegative atoms that can pull on the electron cloud. And each of these pulls the electrons away from the hydrogen different amounts. They call this de-shielding the proton. And what they mean by that is that the electrons are being pulled away from the hydrogen. The more the electrons get pulled away from the hydrogen, the higher the resonant frequency is for that particular hydrogen. And the higher the frequency is, the more to the left that particular environment is going to show up. Let's take a look at these here. I like these pictures. I grabbed them off the internet because the reason I like these pictures is because of the color coding, see? So we're looking at the hydrogens and we're looking at the environment of the hydrogens, which means the carbon that it is attached to. So you can see these three hydrogens right here. These hydrogens are attached to this carbon over there. And you can see here they are, this green part of the spectra right here. And then you have the ones that are colored black here. And so that's these ones right there. And then you have these ones that are blue. And so that's these ones here. Now, the bromine here is a highly electronegative element, right? And so that bromine is going to be pulling on the electron cloud. Notice that the hydrogens that are bonded to the carbon, right here, the blue ones, this carbon is also bonded to that bromine, isn't it? And so the electron cloud is being moved over, is being pulled on by the bromine, and that is what's causing these electrons to vibrate faster. See, these ones here are vibrating faster. The signal that you see down here is backwards. Do you notice that? Here's 0 over here, and there's 11 over there. So the signal is actually backwards. And the faster it's vibrating, the more to the left that is going to appear. And then let's take a look at ethanol. And so you can see ethanol is CH3. Whoops, that didn't come out a very good 3. And then CH2, and then there's an OH attached to it, right? And so the CH3 here, you'll see they have that pointed out right there, okay? So that is what we would call an environment. So this is an environment where hydrogens are attached to this carbon, right? This would be a different environment right here for the CH2. And you see there's CH2. It is in a different environment. And then this hydrogen over here that's attached to the oxygen, that's in a different environment. So the environment is different because the hydrogens are attached to a carbon, and it has to do with what is that carbon attached to, because that is going to cause the disruption of the electron cloud and make it in a different environment. Okay, that's the way I'm using this word about proton environments. So in these spectras that you analyze here, I want you to focus on two things, all right? These are the two things we're going to get out of it. And one of the things that students have, beginning students with this have, one of the problems that they have is that they spend too much time trying to figure out, okay, this is a shift of about 1.2, so I wonder what that is. And they go look at tables to try to figure out what is this shift of a 1.2. I'm going to tell you that's not what you want to do. In fact, if you have tables that are telling you this stuff, you need to just ignore those. You don't need the tables to tell you about these carbon environments. Trust me, they are far more complicated than that. So we need to focus on two things. The first thing is we need to focus on the number of environments. So looking at this first one with ethyl acetate, what my eyes see is that there is 1, 2, 3 peaks. A peak is like a cluster of atoms. So an environment is like any cluster of atoms. So I see, or a cluster of peaks, I guess. So I see 1 cluster of peaks, 2 clusters of peaks, 3 clusters of peaks. Each cluster of peaks is another environment. This is telling me that the hydrogens that are in this ethyl acetate are attached to carbons in 3 different settings, 3 different places, if you will. 3 very unique places within this atom, all right? So that's the first thing I want to focus on. Let's take a look and put our eyes down here at this molecule with this arene ring. Notice with this one that there's only 2 environments, right? There's one environment here, and then there's another environment there. Why only 2? It looks like there should be more places. You know, there's a lot more carbons that this is attached to. And while that is correct, if things look very symmetrical or the carbons that are attached here are the same, if they're attached to the same other things, then they will appear the same. They will cause the same shift with their protons. So, like, let's look at that carbon right here. This carbon is part of our resonance, the arene resonance, and it's attached to what? It's attached to this carbon, it's attached to that carbon, and then there's a hydrogen on it, right? Look at this hydrogen right here in this carbon. What is that attached to? It's attached to this carbon, it's attached to that carbon, it's part of the resonance of that arene, and then it has a hydrogen. See, every one of these hydrogens here, the blue ones, if I were to describe those hydrogens, they would be bonded to exactly the same things. So their environments are not unique. They have similar environments to each other. And we'll see a couple more of these. Another one that we're going to see that's similar are these carbons right here, yes? So looking at these carbons, each of these carbons is bonded to an arene and it has 3 hydrogens on there, right? So both of these are similar to each other. Both of these are the same as each other, and that's why it results in just 1 peak rather than 2 different peaks, right? So this, we would say, only has 2 hydrogen environments, even though I have many places that hydrogen is bonded to, right? Okay, let's talk about the second thing that we need to focus on with the spectras. So that is how many hydrogens are in that particular environment. We can get that information from the height of the peak, how tall the peak is. And it's not always, that's kind of a mistake in saying that, because it's not always how tall the peak is, it's how tall the integration of the peak is. I got to explain that for a second. So the higher the peak, then the more hydrogens is what I'm trying to say, but it's the higher of the integrated peak is equal to the more hydrogens. This spectra up here is not integrated, okay? This is a classic spectra right here. And you'll see that with a classic spectra, you have many lines, right? It's not just one line, it's like many lines that make up each of these clusters of peaks. This is just one peak, but it's like a cluster of peaks, isn't it? Now, those of you who have had calculus, you know that when we integrate something, It's taking what we call the area under the curve of the graph, right? So this thing isn't just like a peak that goes up. This is like a curve. And then what the computer can do is it can measure the area under the curve. And for this one, it would do the same thing. This is a curve that goes up and it comes down, and then it's going to measure the area under the curve, right? Same thing for this one. Now, this curve is not very wide, but it's very tall, isn't it? This curve is fairly wide, but it's not as tall. If you'll notice up here in the color-coded picture, here is the blue environment, and it has 3 hydrogens on it, yes? Here is the green environment, and it also has 3 hydrogens on it. So how am I supposed to tell that these two have the same number of environments, or the same number of hydrogens in each environment? That's where integrating the curve comes in. And because this one is wider and shorter, and this one is skinnier and taller, the computer can look at these and integrate them and be able to come up with a relative amount for each one of these. Now, this is expressed in a number of different ways depending on the particular machine that's being used and the computer software that's being used. Many times in these non-integrated graphs like this, they will have some type of a feature on here that will tell you. I've seen it like this before, where they draw something like this. And that kind of looks like an integral thing, if you're familiar with calculus, right? Kind of looks like an integral. And so they will put this integral sign on here. And when they put the integral signs with these, I've seen sometimes where they make the size, the physical size of the integral sign relative to the area under the curve, or relative to the number of hydrogens that's there. So like these ones here would be 3 times bigger than this one is. See there? So they're you would literally pull out a ruler and measure these things and see how big they are, and then compare their relative heights to each other. So that's one way that a computer might express something like this. It may give you these little integral bars like this. And physically, you use your ruler and measure them. On an IB test, you get a ruler, and physically you have to measure these in order to figure out and say, well, this one was 2 centimeters and this one is 6 centimeters. So I know that this one has 3 times more hydrogens than that one. Follow me? Using a ruler to figure that out. Let's see. Another thing that they do is sometimes they'll just put a number here. So maybe they'll put a number 1 there, and they'll put a 3 here, and they'll put a 3 there. And that would let you know that, hey, there's 3 times more hydrogens in the green environment than in the red environment. Or it would let you know, hey, the green environment and the blue environment have the same number of hydrogens. So these numbers like 1, 2, and 3 are all relative numbers. And so they don't necessarily, in this particular case, are telling us that there are 3 hydrogens here, right? But again, they're relative numbers. All right, let's take a look at this one. This one down here on the bottom with our arene, this one is an integrated one. So this one is integrated. And this one is not integrated. Okay, so the ones that is integrated, you don't see the multiple peaks with this, do you? You just see one peak because it's integrated already. And now the height of this bar is relative to the number of hydrogens that are in that environment. So you can see in the red environment, we have 6 hydrogens in the red environment, and we have 4 hydrogens in the blue environment. So that's why the red peak is taller than the blue peak, because in an integrated graph, the height of it will be relative to the number. Now, if you measured this, then this one could measure, I don't know, 2 maybe. If you measure it 2 centimeters, I don't know. And if you measured this one, this might be 3 centimeters. So literally you pull out your ruler and measure it, and it would be like 2, and this one would be 3, right? Or maybe they would put some number on the top of it, and they would say, this is 1, and this one is 0.67, right? Would that be 0.67 then, or 0.33? I don't know. 1.5? I'm not good with my math. But they would put numbers on the top, and they would be relative to the heights of those particular bars that are sticking up. All right. So let me just summarize this, because I went through a whole bunch of stuff and your head's probably spinning. We're going to be looking for 2 things. We're going to be looking for the number of environments, how many clusters of peaks. That tells us how many, how the hydrogens are dispersed inside of the molecule. And the second thing we're going to look at is we're going to look at the height of an integrated peak. And the height of the integrated peak is relative to the number of hydrogens that are in those environments. Okay, let's practice this a little bit. So here's some molecules. We already did this one, but this one's good because I want to show you a different way that they're integrating it here, okay? So the integration is right here. See that? That is the integration right there. And so the height from this line up to this line, the height right here, that is what gets measured. And again, it's either you take a ruler and sit down and physically measure it, or they would put some number alongside of this to let you know. And notice how this one is taller. So this one is taller in height than that one is. And so you can measure those 2 and come up with a ratio of them. So it's just another way that this could be integrated. This one is integrated as well. So all of these are integrated the same way. And so I'm looking at 2 things. How many environments? I see 1 environment. I see 2 environments. Okay. You say, well, I saw 2 environments over here. That's right, you did. And again, the mistake you don't want to do, throw the table away. You don't want to sit down and say, all right, well, this one is at about 2.25. So I'm going to go look that up and see what's about 2.25. That is, you don't need to do that. We just need to know how many environments are there. Now, how many environments do you see in this molecule? Well, I definitely see this one, right? That environment is in this molecule. And then I see this environment, but it looks like 3 environments, doesn't it? 1, 2, 3 environments? Well, if you pay attention to these 2 carbons right here, this one and this one, you'll see that they look very similar to each other, right? What? They're all bonded to this carbon, and this carbon is bonded to that CH2 and this Cl over here. These 2 are bonded to a carbon exactly the same way. And so these 2 CH3 groups are exactly the same environment. So that's why we only see 1 peak for these 6 hydrogens and then 1 peak for this CH2 right here. So notice that this peak is taller, yes, taller, and that's probably these 2, isn't it? It's probably those 2. And then this peak is shorter, and that's probably this. And if we looked at the integration, the height of this right here is probably 1/3 the height of that, yes? So if I measure this and it's 1 centimeter, I come over here and measure this and it's 3 centimeters. Does that mean it's 3 hydrogens and 1 hydrogen? No, it doesn't mean that. It's the relative numbers of hydrogens. There's 6 hydrogens here and 2 hydrogens there. Yes? So it's in a 3-to-1 ratio of hydrogens in these 2 different environments. All right, let's take a look at this one. We got to get to go a little faster here. So I'm looking at this, and again, I'm looking at the number of environments. I see 1 environment, I see 2 environments. So I can see up, here's some hydrogens right there, and here's some hydrogens right here. And you say, Mr. Hicks, those look almost the same. They look almost the same, but they aren't quite. You see, this carbon is bonded directly to an oxygen there, isn't it? Whereas this carbon is bonded to another carbon. So even though they are similar to each other, they're both methyl groups, the carbons in which those hydrogens are bonded to is bonded to something else. And that changes the shielding. It pulls on the electrons differently, which causes these hydrogens to be deshielded different amounts and causes them to vibrate, resonate at different frequencies. So here we are then. So I have 2 peaks. Now you're like saying to yourself, well, how do I know which peak is which? It really doesn't matter. We just need to know that there's 2 different environments. And the other thing we can get from this is that both of these peaks are like the same height, aren't they? Since they're both the same height, and look at our integration here. The integration height is the same for both of them. That would tell me that there's equal number of hydrogens in these 2 environments. See? So I'm looking at the number of environments, and I'm looking at the relative number of hydrogens in each of those environments. I don't have to know that this peak is this group and this peak is that group. That's not what I need to know, and that's why you're going to throw that chart away, because it'll just confuse you if you sit down and try to figure that stuff out. Okay, let's take a look at this one. Again, 2 peaks. 1 peak over here and 1 peak over there. This one's integrated a little differently, though, so I want to talk to you about how this one is integrated differently. So when I'm looking at this one, I'm saying, what, 2? Only 2 places? Yep. And you're like, well, I see like 4 of them. Well, notice that these 3 over here, they are all bonded the same, aren't they? I have 3 CH3s, and they're all bonded to the same carbon here, aren't they? So all 3 of those environments are really the same. This hydrogen is bonded to a different environment, and it's bonded only 1 hydrogen to this carbon, and this carbon is bonded to a double bonded oxygen up here, which is definitely going to cause a large shift to that hydrogen. So 2 environments, yes, there are. And it also is saying to me, hey, I have a lot of hydrogens in one environment and not many in the other environment. And you'll see here that I have, 9 hydrogens in this environment and only 1 hydrogen in that environment. So with this one, they actually put an integration number down here. You see that? So these are the relative numbers that I'm talking to you about. So if I take this, this number here, it looks like about 155, right? And then I divide it by that 17 over there. I don't know. Do you think I'm going to get about 9? I think so. I don't know the exact number, but 10 times 17 would be 170. So this is looking like it's about 9 to 1. Yeah? About 9 to 1. And so that's how I can use those integration numbers here to come up with what is the ratio. See, 9 hydrogens to 1 in the environments. Let's try that again. So let's come over here. And this time, though this is looking a little weird to me, I actually see 3 environments. I see one environment there, and then each of these is an environment. Now this is an integrated graph, so I'm not getting all the duplexes and triplets and all of the other different types of graphs that are produced from this. It's an integrated graph. And so those two, even though they're very close to one another, they are different from one another, huh? Okay, so if it means 3 environments, where are they at? Well, here's one environment, right? Here's another environment. And then again, I think we've seen this a number of times now. These two are in a similar environment, right? They're in the same type of environment because both of these carbons are bonded to the same carbon here, aren't they? Okay, so this has like 6 hydrogens in this environment. And then this environment has 1, and that has 1. Again, I would sit down with these integrated numbers to come up with a ratio, right? So 7.7, 7.5. They're just a shade bit different from each other, but that's pretty close to just 1 to 1, isn't it? And then this is 45, so 7 to 45, so almost 46, huh? So if I say, okay, I got 46 to 7, what would that ratio be then? 46 to 7, 46 to 8 or so. And are you seeing that it kind of looks like it's what? About 6? Because this is really 7.5, 7.6, something like that. So it looks like it's about a 6 to 1 ratio or so, huh? Because like I said, this is really like 7.5. So this looks like it's about a 6 to 1 ratio to me. And again, you could also measure these. You could take a ruler out and measure the height of that and say, okay, that is about, 1 centimeter. And then you'd measure this one and you'd say, oh, that's about, 6 centimeters or whatever. So you could measure. That's another way. All right, last one. Looking at numbers of environments. 1 environment, 2 environments, 3 environments, 4 environments. Okay, so can we see them up here on our graph? There's 1 environment. Here's 2 environments in the structure I meant. And here's 3 environments. And there's another environment. And I noticed that this one, these 2 are probably together, huh? That's probably all 1 environment right there. Okay, so I found my 4 environments. And then again, I can play with these numbers here. So 37 and 75, that's about 2 times bigger, isn't it? So let's see, that would be 3, and this one is 6. So yeah, that would probably be 2 times bigger. And then this one is 24.8, and it's 2 times bigger than this one. And so that's the CH2 and the O. So they're 2 times bigger of each other, right? And so you see how I'm sitting down and I'm comparing these numbers, and that's telling me about the number of hydrogens in each of these environments. Okay. So let's see how we really use this. Because so far, I'm giving you everything. I'm giving you the structure, right? And I'm saying, hey, look at the structure and look at these environments and match them up. But what if I just gave you the molecule itself? So I covered up the picture of the molecule, and I just put its chemical formula there. We could get the chemical formula from other chemical analyses, and it would give us the molecules, the number of atoms in each of these molecules, an empirical formula, right? So now if we're trying to figure out how does this empirical formula, how does it translate into the structure? what I would do from here is I would try to figure out what this molecule sort of looks like. I would draw out some variations, some isomers of this particular molecule. So let's draw these out. I have 2 carbons, right? So I know that there are 2 carbons, and I have 3 hydrogens, but let's hold off on those for a minute. I have this O2, so I have 2 oxygens. Well, could I have an oxygen on one carbon and an oxygen on another carbon? Let's see. So I put oxygen here and an oxygen there. And could I have something like this? And then 3 hydrogens, 1, 2, and then a third hydrogen over here, and then a Cl over here. And you're saying, well, that's looking pretty good, Mr. Hicks, except these oxygens don't have the correct number of bonds to them, do they? See, so that's not going to work out for us here. So this is out. See, we have to come up with a correct Lewis structure based upon the atoms that's given to us. So let's try again. So I'm going to put into play my index of hydrogen deficiency here, right? Remember how to do that? So I could say, hey, I'm going to have 2 times 2 carbons and plus 2, and then minus 3 hydrogens, and and then minus a halogen, and we don't do anything with the chlorine, and there's no nitrogens in it, right? So I'm doing the index of hydrogen deficiency. I did that in a different presentation, so if you haven't watched that, you might want to go see what in the world I'm doing. And then when I take all of these, I got 4, 6, minus 3, minus another one. So that comes out to 2. Divide that by 2. And that tells me that there is 1 either pi bond or ring. Highly doubt it's a ring because there's only 2 carbons in it. So I'm thinking that there's a pi bond somewhere, but just 1 pi bond. So if there's 1 pi bond, and I have 2 oxygens, just follow me here. If I have 1 pi bond and 2 oxygens, then I'm wondering if this is some type of an ester type configuration, huh? So that would be like this, right? And then I would have a double bonded oxygen like that. And then I could have this, maybe my carbon over here. So one rendition would be maybe my carbon over here on this side and maybe my chlorine over here on that side. So would this work out? I'd have my 2 carbons. I would have 3 hydrogens. They would be right here. And then I would have my 2 oxygens and a chlorine. So this is one possibility, right? Another possibility would be maybe if I did these 2 carbons a little bit different. So maybe I have this, and instead of it being an ester, maybe it's a carboxylic acid. So I could put these together like this and put the chlorine over here on this side. See, so I'm coming up with a different variation on this now, right? So I've thought of one way that everything could be bonded together properly. And that was with this ester up here, or kind of an ester-looking configuration. And then another way would be here, where I have some type of a carboxylic acid with this chlorine that's bonded to it. All right, so I can't really think of any other ways to bond this together. Could I have some type of an ether arrangement, maybe? I don't think so. Not with an unbonded, with a pi bond in it. So I've exhausted most of my different ways that I could put this molecule together following normal bonding rules, right? I'm guessing here at this point. These are the possibilities that I think. It could either be this or that. Now, I'm going to come over here and take a look at my HNMR to see which of these 2 it fits with the best. I notice in this one that all three of my hydrogens are all bonded to the same carbon. You notice that? This one I would think would only produce one peak because there's only one environment where hydrogens are located. This one here has two. So here's one environment, right, with these two hydrogens. And then here's another environment with a hydrogen. That better fits with my graph, doesn't it? I have two environments here with my HNMR. I also notice in the integration number down here that the integral here is twice as big as the integral there, which would say, hey, I have probably twice as many carbons in one environment as I do in another environment. And so if I went and took a look at that in my picture, I see, oh, yep, I have two environments, and this environment has twice as many hydrogens as that environment does. See, that's the way we use our clues. We come up with different variations that this molecule could be. We're going to use our imagination and our bonding rules, draw out different Lewis structures, and then we take and use our different tools that we have available. Here I used index of hydrogen deficiency, didn't I? And I used the NMR. And I can use these two different sets of clues to help me decide which one is the correct structure of this hydrocarbon. All right. Well, I hope you've gotten a little more comfortable feeling with HNMR today. And I just want to remind you, have fun with your chemistry. It's a great adventure, and I'll see you next time.